Hi everyone, my name is David. I'm here along with Aditya and Anshul, and we're going to talk about particle swarm optimization in nature inspired computing. Particle swarm optimization, or PSO, is basically a nature inspired optimization algorithm that we take inspiration from bird flocks or fish schools, basically animals in nature that move in groups or herds. Each particle or each animal represents a possible solution, and they search for food or shelter, basically any kind of optimum solution. The particles move individually in the search space and learn from their own experiences. And we take a best performing particle among each group and then evaluate that among the entire swarm. Over time, the entire swarm gradually moves towards the optimal solution based on one single particle. A PSO is simple, fast, and works well for complex optimization problems in machine learning. It's an evolutionary and stochastic optimization technique. The reason why we call it stochastic is because it's very random and we can't exactly predict the model output and how it'll work. But basically, it uses each particle that finds the best solution and evaluates that against the whole swarm. It was first developed by Dr. James Kennedy and Dr. Russell C. Eberhard. Dr. James Kennedy was a social psychologist, and Dr. Russell Eberhard was an electrical and computer engineering. They combined their knowledge of social psychology and engineering to model swarm intelligence among animals in nature. At its core, PSO leverages the power of swarm intelligence and explores each search space and to find global optimizations for various objective functions. Now, Anshul will explain about the algorithm in depth in PSO.
I'm Anshul Rai, and I'm here to talk about the PSO algorithm. In PSO, each individual in the swarm is called a particle, and every particle represents a possible solution. A particle has three core components. Its x vector or its position. This is the particle and where it's currently located. V vector or velocity. This is what determines how the particle actually moves, including its speed and direction. And its P best, which is the best position the particle has ever achieved based on the fitness function. Uh, these particles repeatedly update the values and stop as soon as it reaches the maximum iterations. Moving on, the PSO works in iterations. Each iteration updates positions and checks for improvements. There are four key steps in each cycle. In the beginning, we start with initializing the swarm. So every particle is given a random position and random velocity. From here, we update the velocity. The formula for updating the velocity uses its inertia, its personal best, its global best, as well as its cognitive coefficient and its social coefficient. Uh, from here, we update the position and update the bests as well. Moving on, some key PSO parameters include its initial parameters of which is the swarm size, initial position and velocity, and maximum iterations. The inertia weight is responsible for controlling the trade-off between the social exploration and local exploitation. We also have the cognitive coefficient, which controls how much a particle trusts itself, and its social coefficient, which controls how much a particle is willing to follow the swarm's best solution. So, for example, if W or its inertial weight was high, then the particles will fly widely and explode. But if it's small, it's going to focus more so on what it already knows. Aditya is now going to conclude the presentation.
Thank you, Anshul. On this slide, I'll be illustrating how particle swarm optimization works using a very simple mathematical function, the fitness function, which is f is equal to x square plus 2x plus 1. We already know that this function reaches its minimum at x is equal to minus 1, where f of x becomes 0. But the point of PSO is to let the swarm particles discover this minimum on their own. So let's see how we can do that. Initial setup is having the positions and velocities at given values. The control parameters define the inertia weight, cognitive coefficient, and social coefficient, which Anshul explained earlier. The plot shows that a table shows a table function for various x values, and the graph is a quadratic curve. Initially, some particles are on the right side of the curve, some on the left, but none are exactly at the minimum. Uh, After each iteration of the PSO algorithm, each particle remembers its own best position. All particles track the original globe best. Using the velocity update rule, they move closer to the best known region. Eventually, all particles converge towards x is equal to -1, which is the true minimum. This example shows how PSO works even on a very simple problem. Particles explore and share knowledge and eventually settle at the optimal point. Now that we've seen how PSO works, let's look at where it's actually used. Some applications. First, in machine learning, PSO is widely used for hyperparameter tuning, which means finding the best settings for models. We usually take random values for these parameters, and each value can have an impact on the final trained model. PSO lets us understand the previous simulations and give us better outputs. It helps in feature selection and even training neural networks without relying on gradient-based methods, which take up much more time and energy and efficiency. In robotics, PSO is used for path planning, where a robot must find the safest or shortest route. It also supports multi-robot coordination, allowing robots to work together like a swarm, similar to how the PSO algorithm works itself. Engineers use PSO for power system optimization and structural design. It helps improve system performance while respecting safety and design constraints. In image processing, PSO plays a role in image segmentation, where an image is divided into meaningful regions. And in finance, another PSO is used for portfolio optimization. It helps support market forecasting since it can optimize models based on large sets of historical data. So overall, PSO's simplicity and flexibility makes it suitable for almost any optimization problem, from machine learning to engineering to finance to market systems, etc. Thank you.